Hello, algebra students. We're ready for section 5 of chapter 5. You'll notice thing 1 and thing 2 in this section. There are two cases, two situations you have to check out. But first, let's start with the review of section 4. So pause here if you haven't already worked out the review, and be sure you've worked the review. Okay, I've gone ahead and done the algebra, and I've gone ahead and graphed number 1, but I have not written the final answer yet because I feel like we need to talk about this. This is an OR statement. If you look at my graph, they overlap at equal to 5 and greater than 5. So if this had been an intersection, then our solution would have been where they overlap. But this is an OR problem. So the answer is x such that x is greater than -2, because that's where it's true for one or the other. Now, it's not true for the second part, but it's true for the first part, unless I pick a number over here, and then it's true for both. So when it's an OR statement, you have to pick the solution where it's true for the most possible numbers, because it's one or the other. So that was a tricky question on the quiz. Let's be sure we've worked that out before the test. All right, number 2 is an intersection. We know that by the way the problem is written. So as I work through both of those doing the algebra, we find out that x is greater than or equal to -4, so it goes to the right, and it's equal to -4, less than or equal to 3. So the solution is the intersection of the two. So you'll write it x such that x is greater than or equal to -4, less than or equal to 3. That's the preferred way of writing this problem. You could have written it with the word and, but I always like when it's an intersection to check to see that I could write it with my x in the middle. And of course your inequality is always pointing with the mouth open to the right. All right, let's talk about absolute value, because today's lesson deals with absolute value. The definition of absolute value is the distance a number is from 0. So if it's distance, it can't be negative. So we're taking the absolute value of the result of x plus 3. It's no longer x by itself. The number has become whatever x is plus 3. So because we're taking the absolute value, we have to check it for x plus 3 equals 5. And we also have to check it for x plus 3 equals -5, because the outcome could have been a -5, and then the absolute value turned it positive. This is how we worked these the first time. So the algebra lets you subtract 3 and get 2, subtract 3 and get -8. Another way you could look at this problem, the x plus 3 equals 5 is very straightforward, so x is still 2. But we could have, instead of making the answer negative, we could have said, what if what we put inside the absolute values were negative? What if the x plus 3, remember it's no longer x, it's the result of x added to 3. What if that number was negative and you applied the absolute value and the outcome would still be positive? So instead of changing the answer to negative, you could have changed the input, the absolute, what you're taking the absolute value of, to negative. What you have to be careful with here is to distribute that negative. So it becomes -x, -3 equals 5. Then we add 3. That's supposed to be equals 5. Add 3. -x equals 8. But we don't want -x, we want positive x, and so we multiply by negative. So we end up with the same outcome. I did not show it to you this way because I think I learned it the way I taught it to you, and I think you will see that it gives you the answer most directly and quicker. But they both give you the same solution, and they are both accurate ways of working that problem. I hope that you tried 4 and 5 on your own. Here are those answers. And now let's talk again about absolute value. That I took the time to show you the two ways to work that review problem because of what we're doing today. So absolute value means the distance a number is from 0. So when we say the absolute value of x is less than 3, that means that the distance between x and 0 is less than 3. So we have to check for whether the x was positive or whether the x was negative. Those are our two cases. Case 1, the expression inside absolute value was the non-negative, which means positive, or it was negative. So those are the two cases, and the solution of the absolute value is the union of the two cases. Now beware when we're talking about absolute value. If it turns out that it's greater than a negative number, then your answer is going to be all real numbers. If absolute value is less than a negative number, then it's going to be an empty set. So beware of both of those. Okay, so you flip your paper over and we're ready to dive into some example problems. Now, it's absolute value, and I'm going to show you how to do this my way, and again, the book is going to show you that other alternative way to work these problems. But I feel like my way is the quickest, most direct way of getting the answer. We need to check the absolute value. It could have been a positive 12 or it could have been a negative 12. So I always set the problem up by copying that sign exactly how it is and putting a negative possibility to the left. So if you go through all of these, I'll copy my inequality sign and I'll put a negative 6. I'll copy the inequality sign and I'll put a positive 8. Wait a minute, a positive 8. There's something awkward here. Let's be aware of this problem. Okay, so before we talk about number 3 anymore, let's come on up here. We're checking for both scenarios. So I have to work negative 12 is less than or equal to s minus 3, and s minus 3 is less than or equal to positive 12. So notice I leave the s minus 3 right where it was, and I'm checking both cases. So I'll add 3 to the first one, and s is going to be greater than or equal to negative 9, and I'm going to add 3 here, and s is less than or equal to positive 15. So when I come over to graph, somewhere down here is negative 9, and somewhere up here is positive 15. S is greater than or equal to negative 9, so it's going to the right, and it's less than or equal to 15, so it's going to the left. So it's going to be everything in between negative 9 and 15. It's an intersection, all right? It's what we call a conjunction. It's where the two come together, the intersection of the two. And if you'll notice, when I first looked at this problem, this inequality sign was the Pac-Man or alligator, whatever you want to call it, sort of makes a C. So that's a little way of checking ourselves. If it makes a C, our solution should come together as a conjunction, all right? Again, it makes a C, so I already know before I start working number 2 that my solution should be a conjunction. So I'll check negative 6 less than p plus 4 and p plus 4 less than 6. So I'll subtract 4 from both sides. P is greater than negative 10. My negative sign better stay with it. Subtract 4. See, my negative signs want to hide. P is less than 2. So when I come over to graph, negative 10's down here somewhere. It's an open circle. It's not equal to, and then 2 is up here, and it's not equal to 2 either. But P is less than 2, so it goes to the left. P is greater than negative 10, so it goes to the right. So again, it's a conjunction. The two come together. And in both cases, our answer can be written, and I failed to write my S is greater than or equal to negative 9, less than or equal to 15. That's your solution set there. And then here, P such that P is greater than but not equal to negative 10 and less than 2. Those would be your solutions. So when we look at number 3, I already told you that we know, based on our inequality sign, that this should be a conjunction. This should be an intersection. They should come together. So if it did not ring a bell with you when it was a negative 8, which that's when, if you were listening as I went through setting up the problems, the fact that it was a negative was already awkward, and that's what it said on the page before. Let's go back and read. It says when you have absolute value and it's a less than symbol, it's the very last sentence, the bullet in the box, then we already should know that it's going to be an empty set, because an absolute value that is less than a negative number is going to be no solution. But let's not take my word for it. Let's check it out. So when I put 8 is less than x plus 6, and I also check x plus 6 less than negative 8, and I do the math, x is greater than 2, and subtract 6, and x is less than negative 14. Oh, I can graph this. I can come over here and I can say x is greater than 2. I can find 2 and I can draw a graph going this way. X is less than negative 14. So I can find negative 14 and I can draw a graph going that way. But when you pick numbers, let's pick a number less than negative 14. Let's pick negative 15. When I check negative 15 and I plug it in, negative 15 plus 6, I'm testing it. I'm checking here. Is that less than negative 8? Well, whenever you take the absolute value of any number, it's not going to be less than negative 8, because an absolute value is always going to turn out to be greater than negative 8. So positive 9 is not less than negative 8, and negative 8 is not greater than positive 9. So there's one reason why it's no solution. Let's check the other side. Let's pick a number that is greater than 2. Let's try 3. So when I plug in 3 plus 6 less than negative 8, again, it's absolute value, so we're going to get 9 again, and it still holds true. It's no solution for that problem. So beware of the negative. Right here, that negative is what you've got to be aware of. All right, for the sake of time, I'm going to skip the word problems just because I need to show you how to work the absolute value inequalities first before we really tackle word problems. So the same situation, when the absolute value is greater than a number, I'll copy my inequality sign and I have to check it for the negative because it is an absolute value. It could have been negative. So I have to check for negative 11, and then when I get to number 3 and I try to copy my sign and it's a negative 2, beware, when it is a negative, I'll want to make it a positive 2. Something's awkward here about number 3. So come back up to the beginning, negative 9, check this way, and check it here, and we'll do our math. I'm going to rush through this for the sake of time. Y is less than negative 2, and add 3 and divide by 3. All right, so when we come over here and we graph, here's our negative 2 down here somewhere. Y is less than negative 2, it's going to the left. Y is greater than 4 and not equal to, and it's going to the right. Okay, that's not a conjunction, that's what we call a disjunction, or an OR problem, and that's okay, because when I look at my inequality sign and it's let me erase it again. Look, if I put a line here, I made that into a D. Do you see that? An inequality that's pointing to that direction. If I put a line there, it makes a D. So I already know it should be a disjunction before I ever started working the problem. Same thing here. If I put a line here, it's a disjunction. They should be going in the opposite direction. So when I'm finished and I graph, if they don't go in opposite directions, I know I've probably done something wrong. So let's check. Negative 11, 2x plus 7, 2x plus 7, to 11, 2x. Subtract 7 makes it negative 18, so x is less than or equal to negative 9. Oh, and also doing it my way, you keep from having a negative to divide by and have to flip the sign. So if you do it the way the book does it, beware. Subtracting 7, so we have a positive 4 divided by 2, and we end up with 2. So here's 2, it's greater than or equal to 2, x is greater than or equal to 2, x is less than or equal to negative 9, and so it's going. Okay, and then for the last one, based on the information from the first page, we know it's going to be all real numbers. Common sense also tells me that the absolute value of any number is going to be greater than -2. So the graph of this is going to just be all real numbers like this, and your answer is this fancy R. Have a great day.